Hello students, in this session we are going to study strain energy stored in the spring wire. Whenever we are giving a twist in the material, there will be energy stored in the material, and that energy is utilized when we remove the load, right? That's why these springs are useful, right? You know that they can store a lot of energy. So what energy will be stored, what strain energy will be stored in the material when we are applying an load which is going to extend this material, right? So when there is extension, there is some torque applied on this spring wire and some energy is stored in the material. What energy is stored in the material? That strain energy we want to find out, right? So you know that when we are applying a torque, there is deflection theta. We have already found out torque is WR and theta is this deflection 64 WR square N by G to the power 4. And within certain limit, if we draw a diagram between T and theta, within certain limit, if we draw the diagram between T and theta, you will get this type of diagram, a straight line diagram like this, right? Up to certain limit, say elastic limit, within elastic limit, right? And what is work done? What is work done? What is work done? This is W is the weight, right? So what is work done? I am writing here W, work done, not weight. That is different thing, right? W I am making this type of W so that you should know that this is a work done by the weight, right? This is not this W is different, and this W is the work done, right? This is not this W, this is different. So I am making slightly different W here. Oh, what is the work done? And whatever is the work done by this weight, that will be the energy stored in the material. So what is the work done? You know that the work done can be given in by two terms, that is force multiplied by distance, or the torque multiplied by theta, that is a small work done, right? So suppose I take a small element here, suppose a small element here, should I take this, and suppose this is the small deformation d theta, and this is the torque T, then what is the energy stored or work done in this spring material? So that is a small work done, delta W, small work done or small energy stored, that will be equal to T d theta, right? T d theta, because that is force multiplied by distance or torque multiplied by the angle of twist, right? You know that, right? You have already read in your previous classes that the work done will be force multiplied by distance or torque multiplied by the angle of twist, so T d theta. And what will be the total work done? That will be equal to integration of T d theta, right? From 0 to theta, this is 0 and this is the theta, So this is the integration of this. And what is this integration? This is the area under the curve. So if we find out area under the curve, we will be able to find out the work done or energy stored in the material. So this is basically the area under the curve. So this basically energy stored or work done will be equal to area under T theta curve. So what is area under T theta curve? That is this area of this triangle. You can see here, this area basically, area under T theta curve, this, right? Area under T theta curve, right? So what will be the area under T theta curve? So that will be equal to half base multiplied by height. Height is T, this is T, and this is theta, so half T theta. So work done will be equal to half T theta. This is the area under this curve, and this work will be stored in the form of energy. So this is basically the strain energy stored in the material. So strain energy stored in the material is basically the half T theta. This is the strain energy stored. So we have found out the small work done, that is T d theta. Integration of work done, and integration of T d theta will give the total work done, and this work done is basically the area under the curve T theta, which is half T theta, and which is the strain energy stored in the material. So you can write now U is equal to half T theta, which is equal to half, what is T? WR, and what is theta? Theta is 64 WR square N, 64 W, this is different W, this is different W, 64 WR square N upon G d to the power 4. So by this you can find out the energy stored in the material. So finally solve it and you will get 32 W square, 32 W square R square N upon G d to the power 4, G d to the power 4. So this is the strain energy stored in the material of the wire. 32 W square R square R, it will become R cube N upon G d to the power 4. So this is the strain energy stored in this material of the spring wire, which can be utilized, right? So you should remember this formula of the strain energy stored in the spring wire. In continuation, we want to find out the deformation or elongation of the spring wire, right? We have already found out the angle of twist, we have already found out the maximum shear stress and strain energy stored in the material. Now we want to find out the deformation or elongation of this spring wire. So a term was used, that is delta, that is the elongation of the spring wire. Elongation of spring wire in axial direction, basically in axial direction. We are talking about axial direction, right? Elongation of the spring wire. So this we want to find out now. What is the elongation of the spring wire? You know that the work done or energy stored, the work done or energy stored is given by, what is given by, that is the area under T theta curve, that is okay, area under T theta curve, this we have already read, right? This can also be obtained by using the force multiplied by distance formula, right? Like when there is load applied, when we are applying the load, there is some deformation in the wire. By applying the load, some deformation is there in the wire, right? So we can also use W delta concept here, right? So what we can do is, if we see the deformation or elongation when we are applying a load, there is some deformation in the wire and it is linear within certain limit, that is called elastic limit, that is linear. This is a linear line, straight line. This is linear, similar to T theta curve. Similar to T theta curve, we can draw the W delta curve, and this is the total deformation by applying a total load of W, right? So if we take a small element like this, and find out what is the deformation in this, so that will be d delta. So total work done or total strain energy, the differential strain energy can also be obtained using the formula that will be equal to W multiplied by d delta, W multiplied by the deformation d delta. This is another way of using the strain energy, and this is the small strain energy or small work. We can also say the small work or small strain energy, that is W, weight applied multiplied by the deformation, small deformation, right, in the direction of weight, right? So W d delta is another way, right? So total work done or the total strain energy stored can also be obtained by integration of W d delta from 0 to delta, right? So this can be the another way of finding the work done or strain energy stored in this spring wire, right? And what is this? This is area under W delta curve. This is, so W or delta can also be obtained, W or U can also be obtained by area under W delta curve. So this is also area under T theta curve, or it can be obtained by using the area under W delta curve. This is the same thing. And within elastic limit, W delta curve is also a straight line similar to T theta curve. So what is the area under this curve? What is area under W delta curve? This is again a triangle. So this triangle, where the total weight is W and the total deformation is delta. This area can be obtained to find out the W or strain energy. So strain energy can also be obtained using the formula U equal to half area of the triangle delta W. Or from here you can find out U already we have found out using the T theta curve. So delta can be obtained as delta will be equal to 2U by W. 2U by W. So this is the deformation in a spring wire. We want to find out the elongation or deformation of the string wire in axial direction. So this is the 2U by W. W is the weight applied. 2U by W is the deformation or elongation of the spring wire. Put the value of du by here and you will get the answer. So what will be the answer? So delta will be equal to, the elongation in the wire will be equal to, in axial direction, that will be 64W R cube N by G d to the power 4. 64W R cube N by G d to the power 4. So this is also an important result where we have obtained the elongation of the spring wire in axial direction. So you have to remember this.